Okay, so this week we are focusing on sequences and series, and there are two main types, arithmetic and geometric, that we are focusing on. And so I'm focusing on geometric sequences right now for, what they are, how to determine, what they are, that sort of thing. So first, we do want to make sure that we have our terminology all correct. So especially sequence versus series. So a sequence is an ordered list of numbers with a specific pattern to it. So you may have a list of numbers, but if there's no specific pattern on how you go from one to the next, it's not a sequence. It could just be like a set of numbers. So a sequence specifically is there's a pattern to go from one to the next number to the next number, like the Fibonacci sequence is a very famous sequence. And that one is not arithmetic or geometric. It's a different type, but the most useful ones are arithmetic or geometric. So each number in a sequence we call a term, and we use A to represent the sequence term, and then we use a subscript with what term it is of the sequence. And we always start counting sequences at 1. We do not start at 0. There are occasions when you would start from 0, but generally you don't. So when you're told, the first 5 terms, you're starting from 1. You're not starting from 0. So whatever you're plugging in starts with the 1. And we don't have like half terms or anything like that. So you're just literally that subscript is counting the terms. Infinite sequences go on forever. And so when you're writing a sequence, you'll use the ellipses, the 3 dots, kind of in between to show that it keeps counting. And then you'll give the formula in terms of n, and then you'll use the ellipses again to show that it keeps going. Finite sequences don't have the ellipses at the end because it stops at that nth term. So it may have 10 terms or it may have 100 terms, however many it has, it stops at a specific point, and that's what makes it finite. And you always have to at least give the nth term so you know what the actual formula is. Unless it's asking you to figure out the formula, then they're not going to give it to you. But if you are writing a sequence for somebody else and you're writing in the order of terms, you want to then indicate what the formula is so that somebody else knows how these numbers came about. So today we're focusing on geometric sequences. So a sequence is considered geometric when the ratios of your consecutive terms are the same. So arithmetic, you're adding the same thing to each term. Geometric is you're multiplying the same thing from each term. And to figure out what that ratio is or what the number is multiplied by, you divide. You do the opposite to figure out what number it's multiplied by. So basically, if you have like the first 2 terms, you always take the second term divided by the first. So you have to do it in the order where the most recent term is divided by the previous term. And that division will always result in the same number. So the second term divided by the first term will give you the same number as taking the third divided by the second, and so on. So all of those will result in the same number, and we call that R. And that cannot be equal to 0. So that is this number that we are multiplying our terms by to get to the next term. And so R is this common ratio. So you want to be very careful if you're looking at whether something is geometric or arithmetic, because sometimes, depending on your numbers, it may look arithmetic if you round, but it's actually geometric. So you do have to check both, because it technically, if you have to round to make it the same, then it's not considered, then it doesn't fit into that category. So, if you find that you're multiplying by the same number, but only a rounded number, then it's not actually going to be geometric. So it's got to be exactly the same for it to fit into this category. So to check that something is geometric, check each term, basically do the division, take each term divided by the previous, see if they're the same, the constant, and they have to be the same number, not rounded to the same number. They should be the exact same number. And you do need to check each term because depending on what the ratio is, it may be like they look this, the first few are the same, but then the ones later are not. If it's almost geometric. So you do want to check all the terms that you see are given to make sure that it is constant, that it's the same number. And if there's a verbal description, you want to think about the fact that a geometric is you are multiplying by the same thing each time. So if you've got a verbal description of something going on, you want to ask yourself, am I multiplying each term by the same number? If I am, then it's geometric. So you really are looking at the division between the terms or what you're multiplying by. And if it's the same, it's geometric. So I've got 3 different sequences here, and we're going to determine whether they are geometric. So the first one, 5, 10, 15, 20, and so on. To check whether it's geometric, you are dividing each term. So if I just rewrite this, I'm going to label each term here. So the first one is A1. So that's the first term, so it's called A1. Then we've got A2, A3, and A4. So to test whether it's geometric, you divide. So we're going to do A2 divided by A1. So 10 divided by 5 gives us 2. Then we do A3 divided by A2. So 15 divided by 10. And that gives you 3 halves. So I don't need to check the next one because I immediately see that these are not the same thing. Because one of them, the ratio is 2, the other one is 1.5. So I don't need to check A4 and A3 because I already know that it is not geometric. And it is, in fact, arithmetic because you can see that you're adding 5 to each number in that sequence. So are there any questions on this first example? Okay, so let's take our next one. We've got 27, -9, 3, -1, and then it just keeps going. So again, I'm going to label these as A1, A2, A3, A4. So to check, we're going to take A2 divided by A1. So that's -9 divided by 27. Now, the best thing to check is to, if you can, to make it a fraction. If you divide it and get into decimal, that's where you start running into rounding issues and everything. You really want to, if you can make it a fraction, reduce the fraction. That's the way to go to check these. So -9 over 27 reduces to -1/3. Sorry, I can feel that sneeze coming. Then we want to check A3 over A2. So that's going to be 3 over -9. So we reduce that. That is also -1/3. Yes, thank you, John. And then, so those two match, and we should check the next pair that we have as well, just to be safe that it doesn't want to go off the rails with the next one. So we want to check A4 divided by A3. And so that would be -1 divided by 3. Obviously, that's going to be the same thing. We got a -1/3. So this sequence is geometric. And basically what it means is that to get to the next number in the sequence, you multiply by -1/3. or divide by -3. That is correct. Yeah, that would be the same thing. We tend to think of geometric as what you multiply by, because that's actually how we define the formula as multiplication. So third one here, you guys are welcome to also do this on your own and then put in your answer in the chat on whether you think it's geometric or not geometric. It could be something else. So we've got 5, 1, 0.2, 0.04. And so I'm going to label these A1, A2, A3, A4. So A2 divided by A1 gives us 1/5. Now, because we're dealing with decimals here, we're going to convert that to the decimal form, because otherwise you're going to have a decimal and then you're going to have to convert it to a fraction. So it's best if you've already got decimals in your sequence to kind of leave it as, to put it in decimal form and actually do division there. So then we want A3 divided by A2. We want to see, are we also going to get 0.2? So A3 is 0.2 over 1, yes. That is also giving us 0.2. Yeah, you want to make sure that it's always like I always write down what I'm actually dividing here. So I make sure that my term, the highest of the two terms, is always on top, because it's always going to be the most recent term divided by the previous term. So next one, A4 divided by A3. So that's going to be 0.04 divided by 0.2. And I use my calculator there. I'm not going to do that in my head. You know, I want to make sure that I don't make any mistakes here. And that also comes out to 0.2. So this is also geometric. So you want to make sure that first you're dividing them in the right order, and then you want to make sure that they have to be exactly the same for it to be considered geometric. Are there any questions so far? All right. So now let's look at this in context of a word problem and trying to figure out, okay, what do we actually have going on here? Yes, and yes, even the decimals should be exactly the same. So if decimal, you got like 1.05 and 1.049, then that would not be geometric, because they are different. They round to the same number, but they're not exactly the same. So they have to be exactly the same. The only place where this may be different is in a real world problem, like if you're dealing with money, your terms have to be rounded to 2 decimal places. So in that case, when you're testing, it may not be exactly the same. And so you just have to think about, well, we're rounding because it's money. So you do have to kind of round. It's kind of a situation. If all you were given is a sequence like this, and there's no indication of any rounding, they have to be exactly the same. But in the real world, we do kind of end up having to round, and you want the rounding to be kind of the same. It kind of depends on the situation. Because in the real world, if you have a sequence, you're going to have to round. And so you just have to say, okay, with the rounded, is this basically going to be the same thing? But don't round too much. Like you don't want to, oops, too far. Like the one on the left here, you don't want to round 1.5 to 2. And then say they're the same, because those are very different. You know, you don't want to do too much rounding. So these are in words, and we want to determine what's actually going on here and whether it represents geometric or not. So first one, a tool and die company buys the machine for $175,000 and it depreciates at a rate of 30% per year. So in other words, at the end of each year, the depreciated value is 70% of what it was at the beginning of the year. So we're losing 30% of the value. So you could, when you have a word problem like this, sometimes it helps to actually kind of figure out, well, what are going to be my numbers, figure out some numbers based off of what it's describing, and then look to see if it's the ratio is the same. So if our first term is going to be 175, so to get the second term, we're losing 30%. So that would be subtracting 0.3 away from 1. And this is kind of going back to compound interest, if you think about it, but kind of backwards because we're subtracting. So we're taking 70%. That's where the 70% comes from, is you're losing 30%, meaning you're taking 70% of the previous year. And that's 122,500. And then, okay, you're doing this again. It's depreciating by another 30%. So again, you're taking another 70%. You're multiplying by the previous term. So the previous term was 122,500. So you're taking 70% of that. And Chris is good. He's getting me the numbers in the chat already, 85,750. So you can then check, well, what is our ratio here? And so if you're taking your A2 divided by your A1, so A2 divided by A1, and I'm kind of running out of room here, so I'm going to just not write out what that is. That comes out to 0.7, which, hopefully that's what we wanted. And then A3 divided by A2, you do that math. That's also 0.7. So we do have the same constant ratio here. We are multiplying each term by 0.7. So the keywords that we had there is that it's, when you've got a percent like this where you're multiplying by the percent, it says 70% of what it was previously. Of means multiply. So we're basically multiplying each term by that 70%. So we are geometric. That is following our definition here. We've got a constant ratio of 0.7. So this is geometric. And you do have to be careful because sometimes just because it has a percent doesn't necessarily mean it's geometric. There are situations where you have a percent, but because of how it's worded or how the math is done, it's not geometric. So you can't just assume percent geometric. You have to actually kind of work through what's going on and make sure that you're actually multiplying by the same thing each term for it to be geometric. Yeah, and you can't, if it has the word average, that you can't assume that that is going to be geometric either. You need to actually kind of check out what's going on, because average has, the word average itself has lots of different meanings. Average can mean that it changes, but if you take the average of how much it does each year, like maybe one year you increase by 25%, the next it's 20%, and then you take the average, it's 22.5, but that doesn't mean that it's a constant 22.5 each one. So that word average doesn't necessarily mean it's the same thing each time. It just could be over the lifetime and averages out to that. Your average return on an investment, obviously that's not a percent you're getting every single time. It's just the average of what you've gotten so far. So yeah, that word average, you can't assume geometric. It may be, you could potentially have arithmetic with a an average, I suppose, is if you're adding the same amount each time, it could probably average out to the same amount, So don't associate average and geometric. So second example here, we've got the starting salary for a job is $43,800 with a guaranteed increase of $19.50 per year. So first term, we've got 43,800. Second term, we're adding that 1950. So that's 45,750. And then let's find a third term. So we add that 1950 again, 47,700. So we want to check our ratios to see if they're the same. So A2 divided by A1. So it's 45,750. I just divided in the wrong order on my calculator. So 45,750 divided by 43,800. And we get 1.044520,548. Like this is not going to be written as a fraction. This is just gross. And then A3 divided by A2. So 47,700 divided by 45,750. 1.04262291. So this is one of the situations where while these would round, if we rounded them to this place they match, this is not geometric because they don't match enough because we're not actually multiplying by the same amount each time. We're adding the same amount each time. Because if you compare it to how much you're adding, we are adding the exact same number each time. So when you have something like this where it looks like it could be either one, which one is actually constant? So it looks like we're kind of multiplying by the same number each time, but we are for sure adding the same number each time. So because that one is, exact, that this is arithmetic, not geometric. So if you have like one that obviously fits the rule and one that kind of fits the rule, you want the obviously fits the rule. Now, if it was not arithmetic either, then you might say, okay, this rounds close enough to geometric. But it's very clear when you're comparing these that we're adding the same amount each year, not multiplying. And so this is arithmetic. This is not geometric. And I point this out specifically because I have seen people making this error on the application assignment. So you can't check one and then not check the other. Like if you think it's geometric and it's close, check arithmetic as well, just to be safe. How do I spell that? Arithmetic. It's basically arithmetic, but it's pronounced arithmetic when it's a sequence. So same word, just pronounced differently depending on the context. Yeah. Any questions on either of these two examples? Okay, so let's say you've determined you've got a geometric sequence. What is the actual formula for this? So this is why I said it's repeated multiplication, is because the way we write the formula is that you get your term by multiplication. And it's very similar to compound interest, where you're multiplying by some rate to some exponent. Now, our sequence has n minus 1 because for sequences we start at 1, we don't start at 0. So that our exponent, if you're thinking of like a compound interest formula where your exponent is n, it's not n, it's n minus 1 because we're not starting at 0, we're starting at 1. So we subtract 1 in our formula, basically. And so that is the formula to get any term out of a geometric sequence. If you know the first term and you know what your common ratio is, I could ask you to find the 1000th term and you could do so with that formula. If you're looking at the pattern of what's going on and where that comes from, each term gets multiplied by r. So to get the second term, you take the first, you multiply by r. Then you multiply by r again. So you can see that's where this formula comes from, because you keep multiplying by r. And so you're just getting exponents on that r. And that's where these formulas come from, is that you're multiplying by the same number every time. And then if you look at what that actually means, it becomes an exponent. So if you have a formula that you can find certain terms based off of an exponent, it's most likely a geometric sequence, but you do need to test the rule of a geometric sequence that the ratios are the same. So we're going to basically use this concept to write the first 5 terms of the geometric sequence. So if you're asked to find the first 5 terms, you don't really need to use the formula. You could just multiply each term by your r to get to the next one. So finding my pen here. Oops, I'm in the highlighter. That's why my pen is like, where's my pen? Okay, so we start. Now, when we say the first 5 terms, that starts with A1. So we're already given the first term here, 7. To get the second term, you multiply your first term, the previous term, by your r. So our r for this first example is 4, so we just do 7 times 4. So that's 28. Then our third term, you take the previous term, you multiply by r. So 28 times 4. 112. And so when you're asked to find the first 5 terms, you stop at 5. You don't find 5 beyond what they gave us. They gave us the first term. We got a freebie there. You just need to find the other 4. And so each term, you just multiply by your r to get to the next. So on your calculator, it's really nice because you can just keep multiplying by 4 and you don't have to like retype anything. And so our 5th term ends up being 1,792. So those are the first 5 terms. And when it says to write the first 5 terms, you need to actually do the math. I've seen people write the formula. You need to actually give me the number. You can't just give the formula. You need to actually do the math to get the number of that term. So just writing the formula doesn't count. So now the second one here, we've got we're given A1. So we've got a freebie here. And we need to find A2, A3, A4, and A5. And our r in this case is x over 5. So we're not going to have a single number because we've got a variable in our r. So our terms here are actually going to be algebraic expressions. And for something like this, I find it actually easier to use the formula rather than to keep multiplying by r, because it will just make your simplifying a little bit easier. So the formula is A1 r to the n minus 1. For A2, it's basically just take your previous term times R. That's easy enough. We don't really need to use the formula for that. So it's going to be 4 times x over 5, which is basically going to be 4/5 x, if you want to write it that way. Or you can write it as 4x over 5. You know, whatever looks good to you there. For A3, you can take your 4/5 x, multiply by another x over 5, or we can use the formula, which would be A1 times your R, which is x over 5, times n minus 1, 3 minus 1. So that would be 4 times x over 5 squared. So that would give you an x squared over 25, which you could write it like that, or you can write it as 4 over 25 times x squared. So I'm actually going to do that. So we can create sequences with variables, and you may be wondering, well, why do we do this? Well, for those that are going into engineering, I can tell you that you will be encountering sequences that are using variables because you'll have to do it in calculus, and then it does show up in some of your engineering classes. ET 310, I know it shows up because there are different special types of series that we use to approximate things. So there are series to approximate trig functions with polynomials. And so this is where this is connecting with your future work. You're like, why are we suddenly doing sequences here? Is it actually is something that is useful. Those in computer science, this is more about programming. You know, one thing that you learned this week is about how you can write recursive formulas, but you can also use the idea of a sequence when you're programming. You know, it's very related to some programming skills. So a to the 4th, you can use the formula. It's 4 times x over 5 to the 4 minus 1. So that is 4 times x over 5 to the 3rd. So you would take x to the 3rd, 5 to the 3rd. 5 to the 3rd is 125. So when you simplify this, you get 4 over 125 x cubed. And then the 5th term, same thing. But now we're going to use 5 minus 1. So it's going to be 4 times x over 5 to the 4th. I don't know what 5 to the 4th is. So that one I do have to do on my calculator. Don't have to do that very often. 625. So this will come out to 4 over 625 x to the 4th. Any questions so far? All right. So now that we've kind of worked with using the formula to write the terms of a sequence, we're now got a sequence and we're going to create what that actual formula is. We're going to find the formula based off of what we have here. So the nice thing about the formula, and I'm going to rewrite it again, it's a to the n is a1r to the n minus 1. So part of the formula is finding a1. That's the first term of the sequence. So that's, again, we have a freebie. A1 for our first example here is 81. So we've got that. We know what our A1 is. Next, you have to find R. So that's what we did when we were checking to see if things were geometric. We find R. So a problem like this is we are assuming that this is geometric, but it doesn't actually specify that this is geometric. We're just assuming it is because I threw it in with geometric sequences here, but we should check that R is constant before we just throw it into our formula. So we need to first do that A2 divided by A1 to verify. So that would be 27 over 81, which by 9 is 3/4. And then we should verify that A3 divided by A2 also gives us 3/4. So that's 9 over 27. Did I 27 divided by 9? Oh, that's one. Wait a minute. 1/3. Did I do my math wrong? 27 divided by 9 is 3. 81 divided by 9 is actually 9. Oh, okay. So I didn't reduce. I did that mental math very wrong. Yeah, this is what I get for trying to be all smart and doing fractions in my head. And this is why you check, because had I not done A3 divided by A2, I would have used the wrong ratio here and gotten my sequence wrong. So always good to double check. So we have the same value here. So this means that R is equal to 1/3. So we're told to find a formula for the nth term. So now we just use our formula here. A to the n is A1, 81, times R. So that's 1/3 to the n minus 1. And that's our formula. And once you find that formula, I can find any term that I want. If I want the millionth term, now my calculator's not going to do that, but I could use the formula to at least write what that would be in the formula. So one thing I do want to, to make the connection to our application assignments is that some of the problems on the application assignment, you can find you're asked for a certain term and you can find it very easily by hand by just doing repeated multiplication. But this assignment is not testing, can you just do repeated multiplication on your calculator? Or can you do repeated addition on your calculator? That's not what we're testing here. The assignment is for you to demonstrate that you can use the formulas you're learning. So use the formulas, like here, well, on the left, I just kept multiplying by 4. And that's fine. But on the assignment, the point of the assignment is to demonstrate that you can use the formula. So do what I did on the right. Use the formula to show that you can do that. Write down the formula that you have to create. If they don't give you one, create the formula first and then use the formula, because that will really verify and show me that you can use what you're learning this week. So I'm not testing your calculator skills, basically. I'm testing, do you understand, the concepts? So example on the right, you guys are welcome to do this on your own and type your answers into the chat as best you can, with the formula, it's a little difficult with formulas. Subscripts when you're typing is an underscore. Exponents are the little caret thing. So, and yes, even if you're a technology major, you still have to know, you have to prove that you can do it without technology to be allowed to use technology, because just the ability to use technology does not prove that you know how to do it by hand and that you understand what's going on. So the only place where I allowed you guys to sort of cheat was with matrices, because I do know that using the technology is really important. But for this week, don't just use a calculator to multiply lots and lots of times. That's not what I'm testing. Yes, it does verify you're using the formula correctly by using examples that are easy to multiply. That is true. So you can check your work by doing your repeated multiplication or your repeated addition. That is perfectly fine. But you want to show the material of the week. So okay, so I've got A1 is 80. First number, easy enough. Let's find our R and hopefully I don't mess up. We've got two people that have two different answers, so it's very easy to goof. It's always good to double check yourself. So A2 over A1, so we got -40 over 80, which is -1/2, and then just sanity checking A3 over A2, so that's 20 over negative 40. That also is a negative 1/2. So that is our R. So R is negative 1/2 because that's the constant here. So that means our formula is going to start with 80, and then it's going to be negative 1/2 in parentheses, and then our exponent is n minus 1. If you write n, that is going to be incorrect. So it has to be n minus 1. And you can always test your formula out after you write it by plugging in 1, 2, and 3 and see if you get your correct sequences there. So you can check your formulas. And be very careful that you're dividing these in the correct order. That seems to be a common error, is doing like A1 divided by A2, but it's A2 divided by A1. Something that helps me remember the order for dividing is I think back, well, when we do slope, it's always 2 minus 1. So I just think of 2 divided by 1. You know, it's always like the second one and then the first one when you're thinking about the order of these things. And so if you think math is kind of consistent about that, about the order that we use our numbers if we have 2 numbers, so that can help you be consistent, remembering that you're dividing second divided by the first. Any questions? Okay. So here we're doing something similar with an extra step. So we're going to write the expression for the nth term of the geometric sequence, and then we are going to find the missing term. So we're going to use that formula to skip ahead and find a term without having to multiply lots of times. So this is nice because they give us the first term and they give us R. So interest of time, I'm just going to go to the one on the right. So I do have several more examples. I don't want to run out of time. So we'll just do the one on the right because that has a decimal R, which is something we haven't, worked with yet. So the formula is AN equals A1, so that's 6 times 0.33 to the n minus 1. So that is the expression. When it says the expression, they technically only want the right side. They don't want the left side because the left includes an equal sign. So that's an equation. So they just say, okay, how would you write that nth term? Now we're being asked to find the 12th term. So you just need to plug in 12 for n. So we have 0.33, and that's going to be to the 11th power. And you're going to get lots of decimals, and then I'm going to multiply that by 6. And I get 0.0003032, depending on how many numbers you get. Chris got a lot more digits. He's probably using a more sophisticated calculator than I am currently using. And unfortunately, we can't write this as a fraction. I use the fraction button on my calculator. It's like, nope. It's like, no, you can't. I mean, if you really wanted to make this a fraction, you could take your 0.33 and write that as a fraction, which would be 33 over 100. And then you would have the 11th exponent, and that will get you some giant numbers because you'd have 33 to the 11th, which is giant. Oh gosh, that's a times 10 to the 16. It would just be, it's not 1/3 because this is 0.33. It stops. It doesn't keep going. So you can't just say it's 1/3. This is not equal to 1/3. So you would have to do 33 over 100. And then you're just going to get really giant numbers if you try to take that to the 11th exponent. So the best we can do is just approximate the actual term. And That's why I use the little approximation symbols there, the little curly, you know, if you make a wavy equal, that means you're approximating because it's not the exact value, because the exact value would be what we have above there. Or if we attempted to write it as a fraction, it would just be way too big. We can't do that. So be careful. You know, this is when you just have to round, and then just be careful that you're not turning a decimal into an incorrect fraction, because then that's going to mess up your results. Okay, I want to do the one. Okay, let's do both of these because these are good ones. These are good to kind of get you thinking, you know, it's not just putting on a calculator. So same sort of thing, but on the left, our R is actually an expression with E. And then on the right, our R is actually a square root kind of deal going on. So on the left, we're going to write an expression for the nth term. So a to the n is A1 is 1. And then our R is e to the negative x. And then that's to the n minus 1. Now we could simplify this. So when you have an exponent times an exponent, you can multiply those. So that would be negative x n plus x, because you can distribute. You'd have that negative x times the n, and then negative x times negative 1, and that becomes a positive x. So that is our a to the n. Our expression is e to the negative xn plus 1. Now we're going to find the missing term, a to the 4th. And we're not going to have a single number here. We're going to get an expression. So we're just replacing n with 4. And so we're going to get e to the negative 4x plus x. And that is our 4th term. So it's not going to be a single number. And we can actually add those together. Negative 4x plus x. That's negative e to the negative 3x. So this 4th term is e to the negative 3x. So we can make sure that we simplify everything as possible, but you're not going to get a single number. You're just going to get another expression because we're plugging in an expression for our sequence. And then on the right, I've got A1, which is 2. R here is the square root of 3. And then it's n minus 1 as our exponent. So we're asked to find the 8th term. So a to the 8th, or a8, I shouldn't say a to the 8th, is the square root of 3 to the 8 minus 1, or 2 times the square root of 3 to the 7th. So there are multiple ways we can write this. If we want to write what this exactly is, we can convert that square root to an exponent, which is 1/2. So that's 3 to the 1/2 exponent, and multiply those exponents to get 2 times 3 to the 7/2 as our kind of answer for a to the 8th. Or we can approximate this with whatever this is going to be on the calculator. And again, it's going to be an approximation. You're going to get decimals. So you would take your square root of 3, which again, can't be written as fraction. It's just an approximation. Then you're going to raise that to this exponent of 7. And then you're going to multiply by 2 and try to round as little as possible when you're doing this. And we're going to get 93.530743661. That's as much as my calculator gives me. And that's just an approximation. It's not the exact value. The exact value is, this would be our exact value, something like that, 2 times 3 to the 7 halves. But we can approximate that as a decimal. Any questions? I suppose looking at this, actually, the 2 square, let's see, I could rewrite this as 2 times 3 to the 6 halves times 3 to the 1 half. This is getting some sneaky algebra here. So this could be the same as, let's see, 6 divided by 2 is 3, 3 to the 3rd, and then 3 to the 1 half is the square root of 3. So we can actually do 3 to the 3rd, which is 27, times 2. So we could rewrite this as 54 times the square root of 3. And that actually is an even better way to write your exact answer. So what I did there is I took our exponent as 7 halves, and I basically undid the rule of exponent where if you're multiplying, you add exponents. So I subtracted away 1 half, which left me then 6 halves left over, which then simplifies to 3. And then I could actually end up turning it into 54 times the square root of 3, which is a lot nicer. Question. So answer as an equation is fine. If you are given an R that has a variable in it, then yes, your answer is essentially going to be an equation because you don't have a single number. Otherwise, you're going to either try to write it as simplified as possible or approximate it as a decimal. Okay, I am going to skip here. I had another example in here, but this one is tricky. So this is probably the hardest one that I've got. We want to find the first term and the 6th term, and we are not given R. We are not given A1, so we have to do some kind of sneaky math here. So all we know is A to the 4th and A to the 7th, not A to the 4th, A4, A7. So we want to find the specific terms here, which means we need to kind of figure out what R is so we can figure out our formula, because we're not given our formula here. So A to the 4th is A1 R to the 4 minus 1. That's our formula. We don't know A1, we don't know R. All we know is N. And so that is equal to negative 18. We also are given A7, which is A1 R to the 7 minus 1. And that is equal to 2/3. So I'm going to show you a little trick here. You can take those two equations and we can divide them. So we can do A7 divided by A4. So that would be 2/3 divided by negative 18. And then that is also taking the actual part with the variables. A1R 7 minus 1 is 6. And then A1R 4 minus 1 is 3. And we are going to be basically taking this and solving. So I'm basically creating a ratio out of my terms. The A1s cancel out, which leaves us with 1 variable to solve for. So I've got 2/3 divided by a -18, and we don't want to like approximate this. You want to make it as exact as possible to find R. So let's see, that is going to be 9 times 3. I believe that's going to be -1/27. 1/27. And I'm going to just double check that with my calculator, just to make sure I'm not doing my math wrong. Yeah, -1/27. And then we have basically R to the 6 over R to the third. So we can use our rules of exponents on the right and subtract 6 minus 3. So we get -1/27 equals R cubed. And then you take the cube root of both sides to find out what R is. So the cubed root of a negative results in a negative. Cubed root of 1 is 1. Cubed root of 27 is 3. So we end up with R being -1/3. So even if you are given two terms of the sequence and they're not consecutive, you can still find out what R is. You just have to do this little sneaky thing with the formulas. So now that we know what R is, we can plug that in to kind of figure out what A1 is, because we also need A1 and A6. So let's just take the one without the fraction. That might be the easiest. So I'm going to take my R now and plug it into my formula A to the 4. So A to the 4 is -18. And this equals A1, and now we know R, that's -1/3 to the 3, because it's 4 minus 1. So now I just need to do -1/3 to the third power, which is -1/27. You know, we kind of already figured that out. Multiply both sides by -27, and I can get A1. So -18 times -27, 486. So we have 486 is equal to A1. So that was one of the things that wanted us to find, was A1. So we had to use the information that we got to first find R, and then we can plug that back into one of our formulas and solve for A1. And then the next thing it says is to find A6. Well, now we know A1 and we know R. So now we can use our formula to find A6. So A6 is A1. So it's 486 times R, which is -1/3. And then that's going to be 6 minus 1 in our exponent. So -1/3 to the 5th power, and then multiplying by 486. And this actually, luckily, comes out to a whole number. Otherwise, I was going to use my calculator to convert it to a fraction. But you do that, you actually come out to a whole number of -2. So A6 is equal to -2. So I like this problem because of several things. It kind of shows you the type of problem solving that you can do. And when you don't have like the conventional, like, oh, they gave us two things in a row, they gave us something different. And we had to kind of figure out, well, what do we do with that information? And it kind of introduces a new trick that you may not have known about, that you can divide equations by each other. You know, we've learned about how you can we can add equations to get together. We did that when we were solving systems. We subtracted because that's sort of like solving systems. You can also divide equations to use that to solve. And so this is a new trick kind of in your arsenal that you can use to solve. And it comes in handy when you have things with exponents. Are there any questions? Okay, so hopefully now you have enough to kind of verify what you've done in the discussion, if you've done this discussion yet. Determine what types of sequences the two guys might have. And then this should also be very helpful on the assignment as well. And what I did here goes beyond some of the things that you need to do on the application assignment, but also very important skills for those that have to move on.